that. So the problem is that I had different technical problems when preparing this series of lectures, and so it was not that easy to have all the references written on the document, so I do apologize for that. Now before moving to the proteins, because in the initial program I wanted to show you how you can use DNA elasticity to study proteins, I simply would like to mention that I said that DNA is a good polymer, but in fact it's not so good because the ones that we can manipulate are not that long, so that you can see the interaction between different monomers. And so to see that, a group in Santa Barbara, the group of Omar Saleh, an experiment where it didn't study the double-stranded DNA, but it studied single-stranded DNA. And studying single-stranded DNA is a bit more difficult because, well, first, the electrostatics plays a more important role, but mainly because you have intramolecular interactions. And if you want to study a single-stranded molecule, the problem that you face is that at some point, because of random motion, one A base will find in front of her T base, and they are going to bind, at least temporarily. And so it makes the problem a bit difficult. The way to solve that, you use chemicals that destroy the part of the molecule that are involved in the H bonding, and so like that you could observe the behavior of the polymer where you have some swelling, where you have a repulsion between monomer and monomer. So the size of the polymer when you have when you don't have this swelling, it goes like the length, it was n to the power 1/2, and in the case where you have a repulsion, you have n to the power 3/5. And so I simply want to show you that experimentally you could well describe the system with the expected scaling laws that you expect from this model. And so it's, even though double-stranded DNA is not a good model for that, if you can use with some tricks, you can use single-stranded DNA to study a polymer that looks like more than what was expected from the polymer community that is well using this model with the swelling of the polymer due to monomer-monomer repulsion. Okay, so I'm going to illustrate in the next hour. I'm going to illustrate how you can study proteins with the DNA elasticity. So just to show you, here is double-strand DNA elasticity, and here is a single-strand DNA elasticity, where here you have some interaction between the different bases. And so what you can play on the different elastic property to study different proteins. So tomorrow I'm going to discuss about an enzyme that is a DNA polymerase, that is the enzymes that do copy the single-strand DNA that will serve as a template to produce a double-strand DNA. So just to give you a clue about the idea of the experiment is that at some point you are going to stretch your single-strand DNA to a given point, with a given force. It will have some given extension. Then your polymerase is going to bind this molecule, is going to copy it, and so to transform it in double-strand DNA. So by doing so, you are going to move along this line at constant force, and you are going, when all the DNA will be copied, you will get to that point. It means that the activity of the enzyme will result in a change in time of the extension of the polymer that you are stretching on. Okay? This is a general idea, and in all these micromanipulation techniques, the idea is always the same. You monitor the extension of your polymer in time. The enzymes are going to modify this extension by changing the elastic property, by changing the nature of the DNA, by changing its topology. And you can monitor the activity in real time. Sometimes you can go to the resolution where you can follow a single enzyme having a single enzymatic cycle on a single DNA molecule, if you have the resolution to do that. And so this is a field that emerged 20 years ago, a bit less. Okay. So I'm going to illustrate this by starting from the same experiment that I did describe this morning. So I forgot to write the name of the experiment this morning. So the first the first experiment with the supercoiling where you had the extrusion of the already junction was done by François Allemand. And the guy who did unzip the DNA is Ulrich Bogenmann, and is now in Paris in another place. So at about the same time, the group of Michelle Wang in Cornell, they had the same idea. She had the same idea. The idea is to unzip the DNA molecule. The point is that DNA interacts in cells with different enzymes, and what's happening on the zipper when you have a protein that is bound on a specific sequence. You have all experienced the fact that when you want to open a zipper, that's something that blocks at some point. The only thing that you have to do is to stretch a bit more to open the zipper. So in the fourth curve, if you don't have a protein that is bound along the DNA, you have this black curve that, as I said this morning, is representative of the ATGC content, the local ATGC content. If now you have proteins that are bound, you will have to increase much more the force in order to open the new bases, because you have first to detach the protein that is bound. So here on the red curve you see that each time a protein is bound, you have to increase the force up. Here it was up to 25 piconewton, here it's up to 40, 45 piconewton. Then you increase the force, you cannot open the bases. Here you detach the protein and then you relax the force. And then you go to the next protein and so on and so on. So you have a sawtooth signal in time when you stretch the molecule like that. And each time you see a peak, it means that on your DNA, at this position that you know because you monitor the position of the peak, at each position you had a protein that was bound. Okay? So you can do the experiments and you can study like that the affinity for protein for a given DNA sequence. So in this experiment, in the very preliminary experiment, Michelle Wang studied restriction enzymes. So as I said, there are enzymes that recognize a specific sequence. Usually they cut, but if the salt condition in the magnesium, for example, is not present in solution, it binds but does not cut. Okay? So you can maintain the protein bound without cutting. So it's bound at specific places, and so what you can do now to see if the enzyme has some affinity or does not have a high affinity for a given site, you can repeat this experiment with different protein concentration. So what you have is that you have a chemical equilibrium. Your protein binds to a given site to give a complex. And the way to quantify this in chemistry, you have an affinity constant. That is the concentration of the bound proteins divided by the concentration of protein divided by the number of sites. So you have to adapt a little bit at the single molecule level this concept. And what appears in your ratio is the number of sites where you have a protein bound divided by the number of sites. So this is simply, this term here, this ratio is simply the proportion of sites that are occupied. So what you have to do now is to vary the protein concentration and to see how many peaks you have. So initially you start with no protein. For sure you open the molecule as it was initially the case to study the DNA sequence. But if you have a little bit of protein in solution, they are going to diffuse and some sites are going to be occupied. You are going to increase and at some point all the sites will be occupied, and you have a threshold at some point. And this threshold is characteristic of your protein and is related to that quantity. So the idea of the experiment is you start, you stretch, you see how many blocking points you have, then you go back to the initial point. The zipper closes itself, okay, because you have no more force, so the zipper is reclosing instantaneously almost. And so you increase the concentration and so on and so on. And so you plot the number of the proportion of occupied site as a function of the protein concentration. And like this you can quantify the affinity of a specific protein to a specific site. Okay? This gives you an idea about the kind of things that you can do. So you can, by using some physical means, you can get some information on biochemistry. Okay, that are useful in biology. So in that sense, you have to play between the different disciplines to try to answer the question that interests the other and try to see if the technique that you have brings you information that other people cannot have. I am going to give you another example. That is the regulation of a system that is named God R. So organisms, they do have to deal with the fact that in solution, so this is a system that works in bacteria in École, for example. So bacteria, they have to feed on what they find around themselves. So they digest sugar. So depending on the sugar that is in solution, the physiology, the way to digest the sugar would be different. So here, this will be when you don't have glucose in solution, but when you have galactose, which is another sugar. So you don't want to express the proteins that are going to be used to digest the galactose when you don't have galactose, when it's easier to have the glucose, to use the glucose that is in solution. So the idea is you don't want to express this gene or this series of genes when there is no galactose to be digested. So you have to block the transcription. That is the step where you go from the DNA that you make RNA and where then you are going further to make some proteins. So you want to block this step. So the way it is done, so I'm surprised that this has disappeared in this projection. So the way that you do that is that you take a piece of DNA and you have two sites that are recognized by this protein, and the protein binds to the two sides and it forms a loop. Okay? And this loop is specific to the gene because it turns out that the transcription, so the place where the polymerase that will generate the RNA will start in between those 2 points. So if you had to express the genes, your RNA polymerase will bind here and will read the DNA sequence in that direction. If you form a loop, maybe your RNA polymerase will bind, but since it's blocked here, it will not be able to escape and to transcribe the gene. Okay? It's a way to regulate the activity of genes. And in this system, you see that the way to regulate is in fact to have some mechanical activity. When you have the galactose that is present in solution, then it will detach the two proteins from those two sides. Then you will have a linear DNA with no loop, and the transcription will be able to start. Okay? It's a kind of mechanical control of the transcription and so of the expression of genes. You see that on such a system, if you start to apply a force with optical magnetic tweezers on such a system, if you apply a force, you are going to break the loop, and so you are going to be able to allow the transcription. So, making a loop generates a reduction of the extension. Applying a force may modify the equilibrium in order to extend the molecule. Okay, so you have an equilibrium in vivo where you form a loop or you don't form a loop, depending if you have galactose in solution or not. And in vitro, in our experiments, we are going to play with the force to displace this equilibrium. Is that clear? For those who don't sleep? Yeah? Okay, so when you look at the signal, so where the system is quite simple, that will be open or closed. It's a two-state model. Okay? So what you expect with a two-state model, if you apply a force that is very high, you expect that the protein will be able to bind. You are going to change the equilibrium position to the open state. You have the fluctuations, but basically you don't see anything that changes in time. If you reduce the force, now you see that you explore between two states, fluctuations at low extension, then you go to high extension. So this is closed, this is open. Closed, open, and so on. So you have a two-state system that is at equilibrium, and because you have the fluctuations, because you have the Boltzmann's law, you can go from one configuration to the other. If you increase, well, the signal, the reference signal was that one, high force. Here I move, here we are at higher force, most of the time we are open, here we are closed, and here is the signal where we don't have the protein. So it's flat, so there's no difference between this one and that. This is why we use it. So you see, you have a telegraphic signal if we average over the different configuration. Now you can use your knowledge in statistical mechanics. How can you get the equilibrium constant of the system? Okay, or how can you get the You have a chemical equilibrium. You go between two states. Okay? How can I write that? If you were in solution, you would study something like that, the chemical equilibrium. And this is the equilibrium constant, and this should go like the exponential of minus delta G times beta, where beta is 1 over k. Okay, this is what you expect from your lectures in statistical mechanics or thermodynamics or even some chemistry. Okay, so this is the usual way of writing it, but now we are not working on an ensemble, so we cannot speak about concentration, but we are monitoring a single molecule in time. Okay, so what is the classic assumption there? Following an individual in time is equivalent than averaging over a population. Okay? This is the ergodic hypothesis. And this is what we have. So in order to measure what people do in biochemistry usually, meaning the ratio of the different concentration, we are going to take a long time like this, where we have fluctuations and at different forces. And we are going to see what is the proportion of the time that I spend in the open state, what is the proportion of the time that I spend in the closed state. Proportion in the closed state. Okay? So by following in time the system, we can have access to the equilibrium constant of the system. And you see that here at this typical force of about 0.9 piconewton, we have the concentration of the time that are almost equal to spend as much time open and closed. So the concentration open and closed is about 1. But you have different ways of realizing this. You could do something like that. Or you could do something like that. For the chemists, or at least those who don't hate chemistry, what changes between the two images? I mean, okay, I'm talking about biochemistry, but you may say I go from one state to another one in a quantum system, okay? What changes? It's simply the kinetics. Okay? To go from one state to the other, you have to go over an energy barrier. And this energy barrier, because of the Arrhenius law, tells you if you are going to go there fast or not. If the energy is high, it means that difference in energy is high. It means that you will have to wait for fluctuations that are not common, and so it will take some time before you have a fluctuation that allows you to go over the barrier. And so it will take some time. On the opposite, if the energy difference is small, you can go easily from one side to the other one of the two worlds. And so you can go quickly and the kinetics will be different. Okay? So I will come back to the mechanics later. But this is the system that we have. You have a system that can be in an open state or looped to an unlooped state, and you have a difference in extension. The difference between the equivalent system in vivo, where you would not, I'm convinced that there are some forces in vivo, but just imagine that it's not the case, that you work in a tube, you won't have any force. The difference that we have here is that we add a force. And the force, so initially we have a potential that's like that, we have no force, and if we don't have galactose but you have the proteins that form the loop that are present, the minimum of the system will be the closed loop. Okay? And sometimes I may have some fluctuations that will allow me to go there, but it should be rare, and I may have then quick ones that may bring back here. When you add a force, what you do is to the potential delta G, you add a term that will be plus or minus depending on the references times the difference in A. Okay? So here to this potential, you add something that depends linearly on the distance. So to this potential, you add a line, and the slope will depend on the force. Okay? So you are going to deform this, just like a magnetic field may modify the potential of spins that are interacting in the Ising model. And so we are going to displace the minimum from there, and we are going to pull down this minimum lower and lower. When we will be in that configuration, that is when there is no energy difference between the two, thermodynamics tells you that you are supposed to spend as much time in this configuration as in this configuration. And this corresponds to the critical force where you spend as much time on one configuration on the other one. If you increase the force, now you are going, this minimum of potential will be at much lower energy, and then you are going to stuck in this regime where the loop is open. Okay? So, on the classical thermodynamics vision of equilibrium, what you do is you simply add a slope on your system and you modify that. And so the time spent, the proportion of time spent tells you what the difference in energy is between the two minima of potential, and what the kinetics, the time you spend on each configuration each time, will tell you how much energy difference there is between here and there, and how much there is between here and there. Okay? So by simply following a simple signal in time, the change, the extension in time, you have access not only to the equilibrium properties of your system, but you also have access to the kinetics. Okay? So here is an example of distribution of the time that you spend in the open and closed configuration. So what you do is you take how long you spend on the open position, you go to the next open position, you do how much time you stay there, and then you have an exponential distribution, so you take the characteristic time. And in the end, you have access to the kinetics of the system. So, compared to what you have learned in chemistry classes, and considering the ergodicity hypothesis, you change the concentration that you have learned. Now you monitor the proportion of time in one state. Instead of measuring an equilibrium constant, you divide the times that you get from the proportion of time that you had, and the kinetics constants are given by the average lifetimes. And as I said, even though it's written in French, but as there are some few French-speaking people in the class, it's not that difficult. You have to modify the action mass law here, because now you have the force, and so you have to modify a little bit your action mass equation. Okay. Force does affect also, because when you add the linear slope to the potential, you also modify the height of the energy barrier. So you have to modify the Arrhenius law according to the fact that you have a force. Okay. And in the specific regime that we did study, so in the GAR system, you see that difference in energy with no force, because you can extrapolate your system, is about 10 kT, meaning that if we didn't have any force, since the energy barrier is high, much larger than kT because it's almost 10 kT, then to see a fluctuation where we would see the opening of the loop, would take a very long time. But here, because we stretch, we can go to a regime where we spend seconds, only seconds, in the open state. And so, as you can extrapolate the kinetics at zero force in this system, it means that if there were no force, it would be in the open configuration only for a few milliseconds, whereas it could remain in the closed configuration for tens of seconds. So basically, we will see mainly this part. There is a mechanical aspect also in this equilibrium. The distance between the two sides here is 100 of bases. Okay, typically 105, I think, in the natural system. I told you that the DNA persistent length is 50 nanometers. 50 nanometers is about 200 bases. Okay? So what I told you for the persistent length is that it's something that is below this distance, the polymer behaves as a rigid rod. Okay? So on 200 bases, the polymer is rigid. And here, we only have 100 bases between the two. So in principle, you cannot wait for fluctuations to bend the system. So the loop is really not a natural system. The way this problem is solved and why it's possible to bend our system here, it's because, if you look here, if we don't apply rotation on the DNA here, even though we are the force when we did observe the signal, we have a flat signal. So the loop does not form if there is no rotation. If you apply a positive rotation, so if we overwind the system, it's still flat, we don't form the loop. We must have negative rotation to be able to observe the loop formation. So we need to apply negative torque on the molecule and we need to stretch it. And if you remind what I told you, this is a regime where we locally denature the DNA. So the way the system solves this mechanical problem is that you need to apply mechanical constraint on the molecule in order to be able to locally denature. When it's locally denatured, then the DNA, the single-strand DNA, is much more flexible. And as it is much more flexible, you can then bend your molecule. Okay? So you see that you have a system that is something that works in bacteria, so it's something that is robust, and you have other systems that are similar, where really the signature of the activity of an enzyme, of a system, is mechanical, and you also need some mechanical constraints in order to have the expression of the system. Okay? So there is this interplay between the mechanics and the biology, biochemistry. Okay? So this is a model. You need to stretch and have some negative supercoiling to denature the system, so there is an additional protein that I didn't mention that much that allows to have more efficient bending. Okay? So in principle, this enzyme recognizes some specific structures that are not BDNA. I told you that one of the specific aspects of DNA is that it's a double helix, and so that when you rotate, you form the pleconines. If you remember, I told you that we had curves like that, and here I told you there is about 40 nanometers per turn. This morning I told you that the sensitivity that we have is about 1 nanometer. It means that it's very easy, well, 1 nanometer is when we put strongly on the molecule. In this regime it's a bit less, to be honest. It means that it's very easy to detect the generation of a single turn on the molecule. And this is a job that is performed by some enzymes that do control the topology of the DNA, and those enzymes are called the topoisomerases. Okay? They are able to act on the DNA in such a way that they do modify its topology. So I must find where is the oops. So here is an example of, so there are two types of topoisomerases, one type 1 and type 2, which is not so surprising. So this is a crystal structure of a type 2 enzyme. And so the way it works is that it captures a double-strand DNA, it captures another one, it will cut the red DNA and makes the green one go through. Okay? You have a link like that. Okay? You cut, you separate, and you close again. Okay? This is interesting in our system.
Question is this sort of, does it work equally like in both ways? So if two DNAs are close and topoisomerase is there, it's going to entangle them? Or is it only going to reduce the complexity or not?
There is some, in the end there is some bias, but not always, and those enzymes, I mean, here they are going to control the topology, so I'll come back to the topology yet. How can I move to the next one? Okay. Having that, what it does is that if you take the red and you make it go through the green one, it's equivalent to generate a change in the linking number of 2. Okay, this is why they are called type 2 topoisomerases. A key element is that at some point you need some source energy. So in that kind of system where it's intramolecular, there is bias. So they go only in one direction. Some go in only in one direction. Those enzymes are also important during cell division, because as we said, you have in each of your nucleus, you have typically 1 meter of DNA, 10 microns volume. Okay? So DNA is really entangled. And so if you want to separate the DNA, if you take a large plate of spaghettis, okay, and if you pull to take some, which has to occur during cell division, you are going to take plenty of spaghettis, okay? But in the end, in real life, you want to take the DNA of the mother cell on one side and the DNA of the daughter cell on the other side. So you want to separate them, but you don't want to shear it in order to break it, okay? And those enzymes, they make the system as a phantom one. There is no friction, you can go, you feel there is a blockage, you let go through. And so you don't break the DNA. Okay? This is why those enzymes are used to target cells where you have an anomalous cell division rate, that are the cancer cells. Okay? If you want to limit the cell proliferation, you target those enzymes, because when they are no more active, during cell division you are going to shear the DNA, and so you are going to destroy the genome, and so the cell is going to die. Okay? So those enzymes are used as the target of some drugs during against cancer. Okay? So in that sense, when they feel you have a mechanical constraint, so they won't take the DNA make through because of the tension that they So, I forgot to change the French here. So, they are able to change the rotation inside the molecule, but as I said, it's also possible to have different pieces of DNA going through each other. And so here it's an example, because we think about our DNA that is not circular, but on a circular DNA, we have to say that it's very difficult to do a DNA replication. Because you want to separate the DNA in the end. But you are going to make a copy of 2 strands of DNA that are winding 1 turn every 10 bases. Okay? So if you take a genome like the one of École, that is about 4 million bases, it means that you have 400,000 turns of 1 strand of DNA around the other. So when you are going to make a copy of this DNA, you will have 2 rings that are going one around the other for 4,100 turns. Okay? And so you have to separate that. And those enzymes are involved in this task. Okay? There is a topological problem here that is not that easy to solve, and the topoisomerase is here. Okay. Where am I supposed to press? Yep, that's it. So what's happening in single molecule experiments? This is an excellent system, because here, as we said, each time the topoisomerase will come and will relax 2 turns, okay? Each chemical cycle is a release of 2 turns and you need to consume some energy, then you release 2 turns, so you are going to release twice the 40 nanometers per turn, and so you are supposed to see a change in extension that is about 80 to 100 nanometers. And this can be easily detected. And so as I said, if you are able to slow down your enzyme, you can slow it down by reducing the amount of ATP that is accessible in solution. So your protein will bind to its target, but it requires some energy to have the kinetic cycle, the enzymatic cycle, and so you will have to wait until some ATP molecule will diffuse, bind to your enzyme, and then the catalytic cycle will occur. And so if you do that, and this was an experiment performed by Terence Strick in the beginning of the, when it was in 2000, I think. You wait, you have the fluctuations of your Brownian motion, and here you have an enzymatic cycle. So you see a single enzymatic cycle of a single enzyme acting on a single DNA molecule. Another one, and so on until you relax and you have no more turn. Okay? So you may work closer to in vivo conditions, that is when you have a concentration that is much higher, and then you can measure the number of kinetic cycles that you may have per second, simply by counting. You put your enzyme, you have a relaxation event, so the extension will change quickly now because you're not able to resolve the different steps. And you measure the difference in extension, and you say, well, I have that time, I had that many microns, so I divide by the 80 nanometers that I have for 2 turns, and then I know how many kinetic cycles I had per second, and so I can plot the speed as function of the ATP concentration, which is a typical plot that biochemists do like. Okay? So you can do some biochemistry, and where the physics also plays a role here, apart from providing a very useful tool, because controlling the supercooling in biochemistry experiment is very difficult, as I said. Here we have a tool where, when all the turns have been relaxed, you simply have to rotate the motors to generate new ones. So you can generate substrate very, very easily, and it's a very convenient way to study topoisomerases. So physics allows you to provide a simple system to generate supercools. And here study introduced also a parameter that is a force, and here you see that the speed of the enzyme decreases when the force increases. And this is another typical element that brings that kind of experiment by introducing the force. Each time that you see that the kinetics of a reaction is modified by the action of a force, it means that the kinetic cycle, the reaction, involves some length modification in the direction of the force. Okay? You slow down because in the area you slow, you introduce a term exponential of force times a distance divided by kBt. Okay? If you have a displacement that is conjugated to the force, you will increase the rate, or you are going to decrease the rate. And so the fact that here in this system you see that there is a decrease with the force, it means that what is likely is that you separate the strands, you have one strand going to the other, but in the end you need to close again the DNA strand, and so you need to fight against the force in order to finish your reaction. And this tells you that this last step, where you have to fight against the force, is a rate limiting step, because if you increase the force, you are going to reduce the rate. Okay? So you have to switch between physics and chemistry. I think I have to make a choice now. Well, at least I'm going to show you. There should be. Here it is. You have other enzymes, topoisomerases, that do cut simply one turn. And what they do is that, as you can see here, they are going to bind at some point. Could be sequence specific, but most of the time it's not. You cut one strand. Then you go back to the solution, to the problem of a classical polymer, where you have a single bond that is here, and so you may have the free rotation. So then the DNA may swivel around this point, and so like this you may relax your system. This is to show you what are the different components of it. And so here is the animation. So this was the work done in the group of Nienke Dekker in Delft. So you have your it's an artist view for sure. There are not that many colors inside the DNA, or at as far as I know. So you bind, you rotate, you relax the plectonins in solution, and then your molecule and binds, diffuses, and another one will come, and so on and so on. Okay? And so each time, plectonins relax, plectonins, you have some length that is involved in the plectonin that is not in the full extension of the molecule, and so the extension of the molecule will increase, and so by monitoring the difference in H, you are going to monitor the number of cycles as well. Okay? So you can do some modeling of the results that you get, and you can see what is the influence of the torque. So one of the elements that appear here is that when you look at the relaxation, it's relatively slow. If you cut a piece of DNA that you let it relax, you should get a much bigger slope here. So this means that the fact that you relax more slowly, it means that the DNA inside the enzyme is going to have some friction. Okay, and this will slow down the relaxation. So you can do some more quantitative analysis. I simply want to insist on one fact, that here we have seen that in the Boltzmann term you have to add the fact that you have the force that is playing. Here we have a torque, and so in Boltzmann's law you have the delta G that you have without any torque, and then you must also take into account the fact that you have a torque. So this is quite classic in the sense that this is a way of you do some Legendre transformation when you work from an ensemble to another one in statistical mechanics, but here you see that with some parameters that you are not so used to manipulate. Okay, and then you can study the effect of some drugs on the activity of these polymerases. I want to switch with a last example, so something that is different. That is the case of the RNA polymerase. So the RNA polymerase synthesizes RNA from DNA. So at some point it must read the sequence. And the way it does is that you have double-strand DNA, okay? You must have access to the inside, so keep it. So the enzyme must come here, open, and then it's going to move, okay? But you see that, I need your help. No, that's okay, don't rotate. If now the rotation, the linking number is constant. If now I open, okay, you see that I'm having more interval between the two strands on the smaller part, which means that there I might be able to generate some superpose. So I think I won't do that here. Well, there are here in this side. Okay? If I let it down, in principle, if there was no plasticity in the system, I should be able to compensation. Okay? So, the question here is that if this model is correct, and people knew already that it was correct, when the RNA polymerase will bind into the molecule, it should open some bases. So locally it will change the linking number, but as the global linking number has to be the same, it means that the number of terms that are present in the rest of the molecule is changing. Okay? And so if you change the number of terms in a molecule where you have supercoils, you should be here, and you should be moving along this line, or here you should be moving along this line. So the binding of an enzyme will result in a change of extension. Okay? And this is what's happening. So where you need a little bit of help, it means that if you open negative supercoil at some point, it means that since you must have the linking number that is conserved, because it's not topoisomerase, you should have some positive terms that are added in the rest of the molecule. So depending on if you are here or here, you should see a decrease in extension or an increase in extension. In addition to that, when it will bind, what your enzyme could do also is to bend the molecule. Okay? And if you have a polymer that is extended, up, and if you bend it at some point, you see that you change also the extension. Okay? So you have a combination, when the RNA polymerase binds, you have a combination of the two effects. One comes from the fact that you change locally the linking number, you denature locally, so some terms have to be added elsewhere, and you change the extension also because you bend the molecule. So this is an experiment that was performed by Terence Schreck, who is now in Institut Jacques Monod in Paris. So you see that on negative supercoils, you start, you bind, and basically here the system is very stable, your protein remains there. Okay? If you are on positively supercoil, so here negatively supercoil means you already started to unwind the molecule. So it's quite easy. As I said initially, if you unwind the molecule, you start to separate the strand. So it's an easy configuration for the enzyme, so it will remain open. If now you go to positively supercoiled, so you want to make more turns on the DNA molecule, it will be for sure more difficult to separate the strands. And so in the same conditions, you oscillate between positions where you are bound and not bound, bound and not bound. Okay? And so each time an enzyme binds here, you see a shortening, you detach, it binds and binds, binds and binds. And here, once bound, it remains there. So you can measure the difference in extension in different positions, and then you have the combination of the two, and you can deconvolute because you know that the change in extension on one side and on the other are the same in absolute value but different in sign. You can discriminate between the two and detect how many turns are open inside the molecule, and like that you know how many bases are read by the enzyme when the enzyme binds. Because the number of bases corresponds to the size of the number of turns that you have removed. Okay? If you see that you remove one turn, it means that you have bound to 10.5 bases. Okay? So it's a fraction of that, the experimental result is a fraction of that. But it's something that you can see, and you can also, because you can deconvolute between the two sides of the hat curve like this, you can see how much DNA is. Okay? So you can really use mechanics of the polymer in order to study very specific elements on the activity of some enzymes that are acting on DNA. You can go to more dynamic elements because the RNA polymerase binds to a specific sequence where it has to start the reading of a gene. But what people have observed is that when you look at the RNA molecules that are produced, they do not correspond to all of them do not correspond to the full gene transcription. It's not that you bind a specific sequence, you go to the end of the sentence, and then you detach. What people have observed that you have many very short molecules that correspond to few bases. As if the enzyme was binding, reading some bases, leaving. Binding, leaving. So there are different models that were proposed. So in one of them, the enzyme stays bound at one position and pulls on the DNA. So you bind somewhere, you try to pull, you detach, so you have made some DNA, and at some point, then you go. The other element would be that you have part of the molecule that is flexible, so I would go further, transcribe, but remaining attached. Then I come back, there is a kind of spring in the middle, and it could be also that the enzyme will go forward, backward, backward. So there are different models. So the signature of this one, you have a loop, and if you travel that you are bound, it simply means that you are increasing the size of the loop. So from the previous signal, we were seeing that we would bind, it will shorten, and if we increase the size of the loop, we should shorten even more. And this is what the group of Terence Schreck has observed. You have the volume motion, you bind, this is the opening of the molecule. And then here you go, you have even larger shortening, which means that you have opened even more the bases. At some point you go, then you transcribe, you go to the end, your polymerase detaches into the next event and so on. So here you have some excursion where you scrunch the DNA. Okay, you go, you open, you go back, you open, you go back by staying attached to the initial binding site. Okay, And it's something that allows to solve, that explains why there were some short elements, RNA elements that were produced. So because by the fact that here we are very sensitive when we apply a rotation of one turn, we are able to detect, in those experiments, we are able to detect the fact that you open the loop by a few more bases, statistically 6 to 7 as far as I remember, at least from the École. Okay? So the group of human mice have done similar experiments where you was using some threads, so some resonant energy, fluorescent resonant energy transfer between different fluorophore placed in the different configuration. You basically they got the same result from an optical point of view, but here you see how the mechanics of the polymer once again helps to get some insights into the fine behavior of enzymes. If you have time, one of the very best papers that you can see comes from the group of Steve Block. And this morning I told you that in the magnetic tweezers and in optical tweezers in general, people are able to measure displacement of 1 nanometer, a fraction of a nanometer. Steve Block could measure displacements that are down to angstrom. Okay? So he could solve the resolution, the position of an RNA polymerase up to the 1 base. Okay? Difference between 2 bases, 3 angstrom. He had a resolution of about 1 angstrom. So he could see when the polymerase was moving by 1 angstrom. Okay? Which is an experimental tour de force. Use some French that some can be used also in other languages. With this resolution, you can get to present different models for the motor that the RNA polymerase is, and maybe I will give you a teaser for the next one. What you could say that the RNA polymerase, as it was known by on other molecular motor, is a thermal ratchet, so I'm afraid that here it will not work, the simulation will not work, it depends on the starting point. Thermal ratchet, I remind you that you have a potential and you are supposed to stay in the minimum of this potential. So initially you start here, and in this model, at some point, what does the chemistry inside the molecular motors, and typically in the case of the RNA polymerase, is that here you will get the energy and you are going to a point where you have a potential that is maybe not that flat, but that is where you can have diffusion. Okay? So if here you come here, you have diffusion, you will explore this region, but then at some point you will go back. So if the time where you stay here is larger than the time to diffuse from here to there, but smaller than the time to move from here to there, it's more likely that you're going to end up here, and then here, here, and then here, and then you are going to diffuse and to have some movement. This is the thermal ratchet mechanism, and as you have seen, we are moving in this direction, so the simulation in the end did work. And so Steve Block, with his experiment, could check that the fluctuations that are involved in thermal ratchet are really important and do explain the mechanism of the advancement of the RNA polymerase along the polymer. Okay? And this, I mean, Steve Block did an experiment, some did other experiments on other motors, and this was a model proposed by Jacques Pro, who people who work in the liquid crystal may know. He had an important contribution on that, and it was not that easy to have this idea to emerge, because the image that we have from on biomolecules came mainly, the images that we have from crystallography. Okay? Where everything, all the position of the atoms are there, fixed. So you may think about the movement of some parts compared to the other. But the fact that fluctuations are involved is really not natural to this view that was imposed by the crystallography. Now, there are more and more evidences that thermal ratchet, the diffusion, is important. Diffusion in asymmetric potential is critical for the behavior of the system. So my teaser is for tomorrow that since you have one base resolution, and tomorrow I will speak about how you can mechanically get information on a DNA sequence, as here Steve Block could get a one base resolution, what you can do is you have your polymerase that is able to walk along your DNA molecule, you are able to see at which base you are. If now you are in a solution where you reduce the concentration of the base A. You are going fast because you have many G, C, and U. U is the equivalent of T for the RNA. So you can go fast because you have all the bases you have to place on your polymer. But at some point, you need to add an A base. But there are very few A bases in solution, so you must wait until one will diffuses to the catalytic site, and then you are going to go one step further. So in a solution where you have very few A molecules in solution, you are going to have stops. The molecule will slow down at position that will have to incorporate an A base. You do the same thing with C, G, and U, and then you will have all the positions on the different bases. And so you have access to the code that the RNA polymerase is transcribing. Okay? So you can have information, precise information, much more than the one that I mentioned this morning on the DNA sequence by using those mechanical micromanipulation. Okay? And so tomorrow I'm going to present you a different setup that we developed in the lab to have some information on the DNA sequence, and it was mentioned at some point about also the chemical modification that can occur on the DNA. But thank you for your attention, and I'm ready to answer to questions with a glass of wine during the post-op session. That's the idea. Perfect.
Okay.